Vertex Buffer Objects allows you to store Vertex data on the GPU. This allows for more efficient access for processing. To create a Vertex Buffer object, you first call GL_GenBuffers. This function can create buffers for a variety of graphical data, but for this tutorial, we'll focus on one use case, which is vertices. The first parameter indicates the amount of Vertex Buffer IDs to create. The second parameter is a pointer to an array of integers to store the IDs in. GL_BindBuffer creates the buffer and sets it as active. If another buffer was already active, it will no longer be. The first parameter of GL_BindBuffer can be either GL_ArrayBuffer for storing vertex data, such as positions, texture coordinates, and normals, or GL_ElementArrayBuffer for storing the indices to vertex elements. The second parameter indicates the size of the buffer in bytes. The third parameter is a pointer to the data that will be stored in the buffer. The fourth parameter accepts an enumeration that indicates the usage pattern of the data that will be stored. There are 9 possible values. GL_StreamDraw indicates that the data will be provided once by the application and will be used infrequently by OpenGL draw calls, for example, a model that is animated every frame but there is only one instance of. GL_StaticDraw indicates that the data is provided once by the application and will be used frequently by drawing commands. This is good for background objects that have static vertex data, such as buildings and terrain. GL_DynamicDraw indicates that vertex data will be changed frequently and have frequent draw calls. For example, a water surface simulation, where the vertices are updated on the CPU. GL_StaticRead indicates that the data is stored once and will be read frequently by the application. GL_DynamicRead indicates that the data for the buffer is provided repeatedly by OpenGL and will be read frequently by the application. GL_StreamRead indicates that the buffer is provided once by OpenGL and will be read infrequently by the application. GL_StreamCopy indicates that the buffer is provided once by OpenGL and will be used infrequently by the OpenGL draw calls. GL_StaticCopy indicates that the data is provided once by OpenGL and will be used frequently by OpenGL draw calls. GL_DynamicCopy indicates that the data is provided frequently by OpenGL and will be used frequently by draw calls. The next function, GL_BufferSubdata, allows us to update a section of the vertex buffer, such as the positions, normals, or texture coordinates. This function is much more efficient for updating a vertex buffer because it doesn't cause the whole buffer to be reallocated like GL_Buffer data. The first parameter dictates the target of this call. We use GL_ArrayBuffer to indicate vertex attributes. The second parameter specifies an offset into the vertex buffer measured in bytes. The third parameter indicates the size in bytes that the update will replace. The fourth and final parameter specifies a pointer to the new data that will be copied in. As you can see in my example, I have 3 functions that create vertex buffers for 3 types of data combinations. To render the vertex buffer data, we first set the buffer as active by using the GL_BindBuffer functions. We then call the pointer functions for the vertex, normal and texture coordinates to set where in the buffer the corresponding data is. This is the final parameter for each of these functions. The GL_VertexPointer function's first parameter specifies the number of coordinates per vertex. This can be 2, 3, or 4. The second parameter specifies the type of each coordinate. It can be GL_Short, GL_Int, GL_Float, or GL_Double. The third parameter specifies a stride for accessing position data between byte offsets. This is needed when you have your position data stored with normal or texture coordinate data within one array and the data is interleaved. We bind the indices, and then we call GL_DrawElements to add them to the command buffer for rendering on the GPU. The first parameter of draw elements specifies the rendering mode. This can be lines, triangles, or patches. The third parameter specifies the type of value in the indices. It must be GL unsigned byte, GL unsigned short, or GL unsigned integer. The fourth parameter specifies a pointer to the location where the indices are stored. To free the memory allocated for a vertex buffer, you call GL delete buffers. The first parameter specifies the amount of buffers you want to delete, and the second is a pointer to an array of IDs that determine which buffer will be deleted. As we now look at the Vertex Buffer Manager module, you can see that I have encapsulated a vertex buffer and index buffer pair into a class that only the Vertex Buffer Manager has access to. The Vertex Buffer Manager class creates buffers for each model that benefits from this optimization. It stores the Vertex Buffer ID pairs in a hash map structure with the model file name as the key. If the model has already been allocated an ID, it sets the corresponding values in the model file. Otherwise, it creates the IDs in the aforementioned functions. The free buffer function frees the buffers associated with a model. The free memory function deletes all the buffers that have been allocated.